So we're going to work on some more applications to solving right triangles. The first type of application we're going to look at here is dealing with bearings. Now these aren't like wheel bearings or things, little ball bearings. These are instead directional bearings. And so when you have, say, boats at sea or planes traveling, they use a bearing to represent the direction in which they're headed. There are two typical ways to represent a bearing, or a direction. One of them is basically a degree measurement clockwise off of north. Okay, so for instance, if you consider a set of axes that have north, south, east, and west on them, then you could represent bearings. One of the ways to represent bearings is just a degree measure clockwise from north, okay? And so a bearing, for instance, of, let's say 20 degrees would simply be a 20-degree angle coming over from north to the east in the easterly direction, okay, or clockwise. You could also represent, let's say, in a similar way that we could do a bearing of I don't know, 290 degrees, for instance. If you had a bearing of 290 degrees, then from north you would rotate 290 degrees around the circle clockwise. So you'd go, this is 90, 180, 270, there'd be another 20 degrees in the in that sort of the second quadrant there, the northwest quadrant. So this would be a 20-degree angle coming up from the west, but all the way around, that would be 290, okay? So it's a bearing of 290 degrees. So the bearing is always represented by a clockwise rotation from the northerly direction, okay? Now, if the, oh, I missed my arrow there. Anyway, the second way to represent a bearing is to represent it using two directions, first a north-south and then second an east-west, and then listing only a direction or an angle measure between 0 and 90 degrees. Most of us are more familiar with acute angles, between 0 and 90. And so if we only use acute angles, that can be a little bit easier to represent. Now, or a little bit easier to understand, I should say. And so in these two examples, the second way to represent the bearing in this first one is to start at north and to rotate east 20 degrees or 20 degrees toward the east. And so we would represent that as north 20 degrees east. Okay, so you start north and rotate 20 degrees toward the east. Okay, so the north or south direction is listed first, the east-west direction is listed second, and the angle that you come off of north or south is listed between them. All right, in the second example here, the bearing of 290 degrees would actually be the angle coming off of the north direction toward the west. So you would have north followed by west, and the angle that goes between them is the angle going from north to the bearing. And in this case, because there's 20 degrees coming up from the west here, that would leave 70 degrees, because these have to be complementary, that would leave 70 degrees here as your bearing off of north. So it's north 70 degrees west is the same as a bearing of 290 degrees, okay? So if I wanted to, let's do another example. Let's say I wanted a bearing of south 35 degrees east, that means you start south and then swing 35 degrees toward the east, okay? So instead of going south, you would be going 35 degrees toward the easterly direction, north, south, east, and west. So this angle here is 35 degrees. That's south 35 degrees east. Now, if you wanted to find the bearing in the other notation where you just go clockwise off of the north, you would be looking for the angle coming down from north into that southeast quadrant, which would be this 90-degree angle plus the remaining between the east and the bearing, which is of course 90 minus 35. Okay, so these two have to be complementary. 90 minus 35 is 55, and so this portion, let's write it in here, this portion is a 55-degree angle, and so 90 plus the 55 would give you 145, so it's a bearing of 145 degrees, okay? So again, two ways to represent bearings. Typically they come off of the north or the south, and again, you can either represent them as a single angle somewhere between 0 and 360, where you just swing from the north clockwise around, or you could represent it as an angle between 0 and 90, an acute angle, which we're more comfortable with probably, and going either from the south to the east or west, or from the north to the east or west. Okay, now let's put one of these examples to use. I think maybe the harder one to get used to is the one where you put the cardinal directions in the bearing. I think the other one is a little bit more, may at this point be a little more familiar because we're dealing with those angles from 0 to 360 so often. You just have to remember that it's coming off the north side rather than what we typically and going going clockwise, rather than what we typically use as the x-axis going clockwise. Man, I said that backwards. Rather than going from the positive x-axis going counterclockwise. Okay, I can't speak for whatever reason right now. Okay, so a quick example of this. Let's say you had two boats and they leave a port or a city, okay? This is the kind of problem you'll see in the textbook. They're a little bit, manufactured, I suppose you could say. They're a little phony, but they work out, so it's just good practice with these problems. So one boat, let's say it travels in a direction of north 32 degrees 20 minutes east. Okay, so there's north, south, east, and west. All right, so that's the first boat. The second boat travels from the same port, and they leave at the same time, going in a direction, we'll call this one south 57 degrees 40 minutes east, okay? And then the two boats are traveling at different speeds. So let's say the first boat is traveling at 30 miles per hour and the second boat is at 25 miles per hour. And so a question might be something like, how far apart are the boats after, say, 5 hours or some given amount of time? So let me write that up here. How far apart are the boats after 5 hours? Okay, So essentially what we're looking for is the third side of a triangle where you have the first boat, second boat connected by a line. That's the third side of the triangle. We're looking for that distance, okay? One thing I note as I look at this diagram, and I always want to draw out diagrams for these, it's just going to help me to sort of organize the different pieces of information on the triangle. And so one thing to note is that the angle here between north and the bearing of the first boat is 32 degrees 20 minutes. So I could write that in. That's 32 degrees 20 minutes. And the angle then between the south and the east is going to be 57 degrees 40 minutes. Okay. And so what we want to do is figure out what are the angles maybe of this triangle, because right off the bat I don't really know what kind of triangle I'm looking at. I'm hoping that there's a right angle in here somewhere, because we're looking at right triangle applications. If I don't have any right angles, this is going to be a much more difficult problem to work through. And actually in this particular case there will be a right angle, we just got to find it. We're not sure just right off the bat. Maybe you can tell a little bit by looking at the diagram, but my diagram could be off. Okay, so in your diagram, if you drew this yourself, it may look completely different than mine. So we've got to do some calculating. So the first thing I'm going to look at, I'm going to switch colors here, is to try to find, I think it's going to be the easiest thing to do is to find this angle here at the city, sort of the difference in the bearings. Okay, so you got one going up to the right, one going down to the right. What is this angle between them? To find the angle between them, you could find the angle above the easterly direction, and you could find the angle below the easterly direction. Okay, those two angles. And if you find those two angles and add them up, you'll get the angle between. Okay, so how would I do that? Well, 32 degrees 20 minutes is this angle up on top, so the remaining angle here that I highlighted in black is going to be the complement of 32 degrees 20 minutes. Okay, so let's calculate that. The complement is 90 degrees minus, I'll do this in the black color, 90 degrees minus 32 degrees 20 minutes. Now we're going to do a little borrowing, because 90 degrees is really 90 degrees 0 minutes. And so I'm going to rewrite that as 89 degrees 60 minutes. Okay, so remember that 60 minutes is really 1 degree. So 89 degrees 60 minutes is the same as 90 degrees. But now I have enough to do the subtraction. So if I subtract my minutes, I'm going to get 40 minutes. And if I subtract the degrees, I'm going to get 57. Okay? So 57 degrees 40 minutes is my angle up here. Well, interestingly, I recognize that as the other angle in the problem here. And so when I calculate my complement for this lower angle that I highlighted in blue, interestingly, it's going to be the 32 degrees 20 minutes, right? You could check that. If I did 90 degrees minus the 57 degrees 40 minutes, of course, 89 degrees 60 minutes and 57 degrees 40 minutes. Subtract the minutes, you'll get 20, and subtract the degrees and you'll get 32. So you will get 32 degrees 20 minutes. Now, because we already know that 57 degrees 40 minutes and 32 degrees 20 minutes are complementary, we just determined that over here twice. That means if they're complementary, they must add up to 90. So if I re-added them back together, I know this total angle here is 90. That gives me a right angle, okay? So what I'm going to do is I'm going to kind of remove this triangle and redraw it over to the side just to keep my mind wrapped around where everything is. It's getting kind of cluttered up here in my diagram. All right, so I have a 90-degree angle here. Again, I don't really know, this angle could really be coming out farther, or it could be coming back, or it could be coming straight down. I'm not really sure. It isn't going to really matter on my diagram in the end. I just need to find the length of that third side. Well, that third side ends up being a hypotenuse because it's opposite a right angle. The two sides, the two legs of the triangle can be calculated because we know in general distance is equal to rate times time. We're given a rate and a time for each of those sides, so I can find the distance. 30 miles per hour for 5 hours is 30 times 5, which is 150 miles. And then the other one is 25 miles per hour for 5 hours, which is 125 miles, okay? So those are our two side lengths. So we're gonna have a 150 and a 125. And now all I need to do is find this hypotenuse, okay? All right, well, the hypotenuse, because this is a right triangle, a hypotenuse can be found from the other two sides using Pythagorean theorem. So I'm gonna go with 125 squared plus 150 squared equals, well, I'll call this C, right? C squared for Pythagorean theorem. And 125 squared, that one I don't know offhand, so I'm going to use my handy dandy calculator. 125 squared is 15,625. And I'm going to add to that 150 squared, which is 22,500. When I add those together, I get 38,125. And I want to take the square root of that. Now this answer is going to end up being an irrational number. It's a long decimal. I'm going to keep, I don't know, we'll round it to the nearest mile, I think, at this point. So then our C value, which is the square root, is going to be around 100, should say approximately here. It'll be approximately 195 miles. Okay, so again, I'm keeping that to round it to the nearest whole number because that's what all my original distances were rounded off to, okay, or measured in. So it's approximately 195 miles between the two boats after 5 hours of travel.